All right, welcome everybody. Let's go ahead and begin. Monday's going to be a big day because you've got an exam, and we talked a little bit about it on Wednesday of this week, but you are allowed to bring 1 page of formulas. It's not a page of notes, so it shouldn't be conceptual information. It should be specifically just equations, variable definitions, and units associated with that. You can have like a problem-solving step-by-step summary if that's what you'd like to include, but none of the information that would assist you in solving a short answer kind of a question. So the exam will have some of both. It will have some conceptual questions that I want to gauge what you actually are understanding and can recall, and then there's going to be some application and problem-solving questions as well. So we'll do that on Monday, and a part of the exam will be a really brief assessment of where things are at with your WMS skill. So you need to bring a computer with WMS installed for the exam on Monday. So does anybody have questions about those 2 announcements, homework and exam? What we're going to do in class today is go through the process of generating curve numbers for the same watershed that we looked at on Wednesday, that watershed that's over by the Huntington Mall. So we'll calculate curve numbers and then use those to run through the TR-55 method. So just to refresh your memory, the location is this watershed that has this stream that runs along Wildcat Road, and it discharges into the Mud River. And the specific location that I'm interested in, if we zoom in, remember that the stream goes under the road at a certain point. And so that would be the location of interest. So what I'm going to ask you to do is I'm going to pause for a moment. I'm not going to talk you through the step-by-step process, but I'd like you to delineate that watershed. And so what that will consist of is starting up the hydrologic modeling wizard, delineate the watershed, and then once you've delineated the watershed, we'll go through the process of obtaining the soil data and obtaining the land use data in order to calculate the curve number. So here's the location. You're on your own for like the next 10 or 15 minutes. I think 15 minutes is plenty of time to delineate that watershed. And that's kind of a good pre-test for the exam on Monday, because I'll be asking you to do the same thing, to delineate a watershed. That'll be part of the exam on Monday. So I'll tell you a location, and here's the location of the outlet. It's where Wildcat Creek reaches that Wildcat Road just north of the mall. All right, so I've just done it. That same approximately 550 acres that we saw on Wednesday. And remember that on Wednesday what we did was we applied the rational method and we did national stream flow statistics. Did anybody write down the peak flow rates? Do you have that in your notes? I don't remember. I think maybe one of them was around 270, the other was around 3 something. It would be easy enough to run that model again real quick, and so let me do that. Let me start up the modeling wizard and select model rational. So the C value that we applied on Wednesday was 0.35. We had it compute the intensity after we calculated the time of concentration. So time of concentration, I used the SCS method for lag time with a curve number of 68 being the assumption. We're going to go and see whether my gut instinct about a curve number of 68, how accurate that is, because we'll calculate the actual curve number in just a moment. But we need some sort of a curve number in order to estimate the lag time and therefore the time of concentration. So going with that, now we've got 46-minute time of concentration, have it compute the IDF curve, and I'm going to get online data with the Hydro 35. It creates these green lines here, which is the IDF and the 10-year rainfall return period. Now I've got, okay, it was higher than I remembered. It's 446. So Q10, according to rational, for the peak flow rate was 446 CFS. And then the Q10, according to National Stream Flow Statistics for the peak, let's just pop that up really quickly. Switching from rational to National Stream Flow Statistics. Open up the model again by double-clicking on that brown icon and switching from Alabama over to the West Virginia equations. Scroll down, it is the Western Plateau 2010 formula that will apply here. And then I have it compute the results based on this drainage area of 0.871. So here, the 10-year return period, it says, is 265. 265 CFS. All right, so we're going to look at it a third way. We're going to find out what's the Q10 according to TR-55. And we'll get the peak flow rate from that as well. But TR-55 requires curve number. And I don't want to just say that most of the time curve numbers in watersheds around this area are 68. We can be more precise than most of the time in my past experience. We can look at what are the actual properties here. So open up the wizard. We need to get some more data. What we've got so far is only the elevation data. And actually, this is a good time for me to save the file again, because you never know when the program could crash, and I want to be able to come back to this point in time if it does. So in the wizard, let's go to the download data, and previously all that we had indicated we wanted it to download was the elevation data. So that's already ticked, but we haven't got the soil type or the land use. So turn off elevation data. We've already got elevation data. We don't want it to go get it again. But turn on NLCD 2011. That's the National Land Cover Database. It's getting a little old. I think that there was a survey more recently than that. I need to check with Aquaveo and see when they're going to integrate the more recent survey, because, you know, in some places there's a lot of development in the course of a decade. And what the land cover database is going to show us is what areas are what kind of land use. It's going to show us certain locations that are woods, certain locations that are road, lake, industrial area. It has a bunch of classifications that we're going to need access to the data. And then there is Surgo soil data. So select that, Surgo. So just those two, and then click Download Data from Web. Now the first thing it's asking is, how big should the cells be for the National Land Cover Database? And the default is 20, and we're just going to go with that. It's the same kind of thing that it asks when you download the elevation data, which is, do you want to resample in order to get a different resolution than it estimates maybe is the best approach. 20 meters is the best resolution for the National Land Cover Database. So we couldn't get any finer than that. We'll just go with the default. And then down here at the bottom, it gives you kind of a progress report of the data as it's being downloaded. So first it's getting the land cover database, and then what we're seeing now, all those black lines, those are the soil type polygons. So look over here on the left side, there's now a lot of new stuff that we haven't had previously. So let me turn off for now the street map, so we can just look at the other stuff. So let me also turn off the soil data, and let's zoom in and see what it looks like when we turn on the National Land Cover Database. So let me turn off the elevation data. All right, so these colors, this is the color that's associated with the National Land Cover Database. And so just remember where we're working. So here's the area that we're working. Let's do some shape recognition and see if there are some commonalities. So here's the Land Cover Database, and here is our just street map. This is Google Maps. Do you notice any common shapes? What's this? The mall. So in red, it's assigning impervious urban areas. All right, now what is this big stretch of red? What does that associate with? That's the Big Bend Bowen Highway. That's the one that connects like the Target Plaza over to Route 2. So this is Target. Here's the Big Bend Bowen Highway. There are some like suburban developments. So each of the different colors means a certain land use. There's a number associated with each color in the background. And so a file that I need to put on Blackboard for you to use, I'll do that in just a moment. But let me show you how we're going to translate that. This is a table that we're going to use to translate those colors into what it is. I made this table more than a decade ago because one didn't exist already for West Virginia. But what it has is different classifications and then the curve number that's associated with type A, type B, type C, and type D, hydrologic soil group soil. So there's a color number 11 means open water. And it doesn't matter whether you've got type A soil or type D soil, the curve number for open water is 98. So you can see that there's a wide range of things. There's barren land, developed open space, developed high intensity. There's all these different classifications. And so the way that it's going to calculate curve numbers, it's going to look at what color do you have. And so this dark green that we're looking at, I think is probably mixed forest. And so it's going to look at the combination of that, and then also turn on now this WV11. That is the soil data for Cabell County. So if you turn on WV11, so now there's all these polygons corresponding to different soil types. So it's going to look at the overlapping soil types along with the land use, and then it's going to estimate the curve number by this table. All right, so give me just a moment. I'm going to put this table onto Blackboard for you and click on it. It might just display it. Yeah, see how it's just displayed it? So instead of displaying it, what we want to do is, I might have to change the file format because you might be able to just right click on it and then save as. Okay, so right click, save link as. Yeah, do that. Right click on it and save link as, because if you just click on it, it'll display it rather than allowing you to download it. Right click, save link as. All right, so this is the table that'll translate the colors and the soil types into curve numbers. Now if we zoom out, what we're going to see is there's a lot more soil data than we actually need right now, because here's Cabell County, but because we're adjacent to other areas, it also downloaded Wayne County soil data, and is that Lawrence County across the river in Ohio? We don't need either. So right click on this shapefile 87 and delete it. Right click on shapefile 99 and delete it. So now the only one that we've got saved in our project is this shapefile 11, which is Cabell County. By the way, let's save our work again. Click on save. So that soil data is there whether or not we're looking at it. We can turn it off if things are getting a little too cluttered. We can also turn off the grid, I think. Yeah, turn off map data, just like, well, display options. Let's leave it on for now. All right, so what we're going to do is there's a little bit of data management we have to do with the soil data that was just downloaded. Let me show you in the folder that we're working in where things stand. I created this subfolder for March 8th, and so it downloaded Friday Surgo, Friday Surgo 2, Friday Surgo 3. Those are the three different soil type counties. It downloaded Cabell County and Wayne County and Lawrence County. I'm not sure which one is the original, which is 2, and which is 3. It doesn't really matter. The main reason we got in here is I just wanted to show you that within any one of these folders, there's a lot of different subfiles. And the shape file that we're looking at is just one of them. So I guess now we can know. So the first one, this is 87, Surgo. Surgo 2 is 11. So 11's the one that I want. So if I was really trying to save space, I could get rid of Surgo and Surgo 3 in my case. Yours may have been numbered differently. But the main point I want to emphasize is that the shapefile we're looking at is only part of the story, because there's a database file as well that has a lot of attributes in it, and we have to link the two. We have to tell WMS to go and get the data that we need. And so here's how you do that. Right click, so we've got the soil data. Right click on the name of it, and instead of deleting like we did for the others, do this one, join NRCS data. So right click, join NRCS data, and so it's going to join the soil texture, but more importantly for us is hydrologic soil group. So this, having that box checked, join hydrologic group, that is what's going to do the magic of telling us whether it's soil A, B, C, or D at every location. Because like if I zoom in right now and I just pick out one of these, if I pick out one of these polygons, I can use the identify tool, and it'll tell me, for example, here I'm going to click on one of the polygons. It says it is GEC. And you remember how when we were looking directly at the soil data, there was like the Gilpin Upshur data. They had those 3-letter abbreviations. So all it knows so far is the soil type. There's not much data associated with these polygons yet. But when we join NRCS data and then I use this identify tool, then it's going to actually know which hydrologic soil group it belongs to. So I haven't done it yet. Right click, join NRCS data, and then fill blank values, because if there's any one of these polygons that doesn't have a hydrologic soil group already associated within the database, I'm going to tell it right now to assume that it's type C soil. And the data quality is pretty good around here. There won't be very many polygons that are blank, but C is a fine assumption if it is blank. So click OK. In the background, it linked the database to these polygons. And so if now I do this identify and click on a polygon, now it's got more data. Before it was just kind of telling me the abbreviation, but now it's got hydrologic soil group, the saturated hydraulic conductivity, the field capacity, moisture content, wilting point, soil texture. There's a lot more data there. And that has to be there in order to calculate the curve number. All right, so any questions? Does anybody need to see a certain point that we did?
I have a question.
Yep.
When I click the identify tool,
Uh-huh.
I click on it, it doesn't pop up that little table thing that yours pops up.
Are you near a polygon boundary? Because I mean, like if I use that soil tool and I click outside of the soil data, I may not get anything.
I clicked on 2 and 3 different colored things, and they don't pop up for me. Like it refreshes on the right hand side, but
Mhm.
the table's over there. It doesn't pop up anything in the middle of the screen.
Well, I don't know why it might be that way. I can take a look at it after class.
No, I got it.
Got it? All right, good. So right now, the soil data is GIS data. We have to create a coverage with that soil data. So we're almost to the point where we're going to calculate the curve number, but we've still got kind of a little bit of hoop jumping left to do. Because right now, our only coverage is a drainage coverage. Let me turn off everything except for the drainage coverage. Shows me the boundaries of the watershed and where the streams are likely to form for the initial like flow accumulation cell area that I'd selected. So that's what is the drainage coverage. I need to create a new coverage. It just means like a new layer specifically for soil data. So right click on the word coverage and do new coverage and choose soil type from the list of options. So we're going to create a soil type coverage, and then all you can do is just click OK. Okay, so now we've got an empty soil type coverage. There's nothing actually in that coverage right now, but we're going to put something in it. We're going to copy over the data from our GIS into the soil type coverage. So go back now to the GIS data, and we can turn it on so that it's visible. And let me, in the background, I can kind of see the boundaries of my watershed. Use this select shapes tool, which is underneath the identify tool. Select shapes and then click at the top left and drag down. So I'm creating a box that's going to encompass all of the polygons that are in or near my watershed boundary. So if I zoom out, like any polygon that's connected to my watershed is included, but then there are some polygons that aren't. So for example, the Mud River was included. So water, since there was a continuous polygon of water that ran through my watershed, now all of them are selected. But anyways, I selected those polygons, and then switch over to the GIS module. Maybe we're already there. And do mapping shapes to feature objects. And select coverage, soil type, map shapefile, select the shapefile that has our soil data. Next. And then just see if it's correctly interpreting the main thing that we want it to map into the soil type coverage for our purposes is the hydrologic soil group. So what it's going to be doing is it's going to be assigning the SCS soil type from that field hydrologic group. So it's recognized that in the background of that database file it had hydrologic soil group, and it's going to be copying all of this soil data into the soil type coverage. So if you click next and then finish, it briefly is going to paste all of that. Now here's the soil type coverage is turned on. So all those polygons are there, and it's going to allow me to calculate the curve number. So now I can switch back to the drainage coverage and see the boundaries of my watershed and just make sure that I have the soil polygons are going through my watershed. They are. I can turn the terrain back on to get those elevation, contour lines, and so on. Okay, we haven't calculated the curve number yet, but we've got everything, all the prerequisites are satisfied so far. How do we know the curve number hasn't been calculated yet? If I turn on the display options and the drainage data, I could display basin CNs, and it's going to say, oh, CN 68. That's because I typed it in earlier. Remember when I typed it in for the calculation of the time of concentration? So it's going to replace what I've guessed as 68 with the actual calculated value here in just a moment when we have it compute the curve number. So to do that, go into the hydrologic modeling module here, this one, and anytime we switch between the modules, the menus at the top are different. So just a moment ago, I think we were in the GIS module because we were working with this GIS data, pasting it into a new soil type coverage. But we want to be in the hydrologic modeling module, and there's a calculator that we're going to use here. So it's the calculators menu. And do you remember where you saved that text file? Because you're going to need to browse to it in just a moment when we compute GIS attributes under calculators. And so it's going to use the soil type coverage that we just created, and it's going to use the land use grid, which is the National Land Cover Database. So use that grid for the land use. And then we need to import the key it should use to associate soil type and land cover with a certain curve number. So now click on import and browse to the location that has that text file. I'm trying to remember where I put it. There it is. Okay, so when you open it, then it'll summarize the table. It's that same kind of like text view. It's interpreted the commas that are in that text file as being distinct columns. So now just click OK, and it's going to calculate the curve number. It can tell you a little progress report at the bottom. And when it's done calculating, it's going to pop up a text file summary. Hopefully it's not going to crash my program. Okay, good. Thank goodness. It was taking longer than I usually see. So it saved a curve number report. It's giving me kind of the summary of the location of that. Doesn't matter for now. Just click OK, and you bring up the report, and we can save this. You know, if I want a copy of it, I'm going to be sure to save as in the location that I'll come back to later. So I've been working in this WMS subfolder for 8 38. So curve number report, I'll save it there. All right, so it's calculated, for example, that there is 2.1 acres of land that is grassland and has hydrologic soil group C. So it's looking at the combination of those two, that there's a certain amount of grassland with soil group C, and it knows from the table that it should classify a grassland with soil type C as 71. And it knows how much, and then it's doing in this column a weighted average. So it's looking at how much area is there, what's the curve number associated with that combination of land use and soil type, and it's computing a weighted average. And so what's the most of this? Like of our 550 acres, 450 of it is deciduous forest. That was that green color that we see so much of. How can I see that again? Well, oh, National Land Cover Database. If I turn on this color, I think I'll see it. Yeah. Let me turn off the soil data. So this dark green was deciduous forest. There's some barren land, type C, not very much type A in this watershed, you know, like 2 acres here, 7 acres there. Developed open space, I guess that would be like the roads. Developed low intensity would be homes. So anyways, it calculated the curve number, and what did it estimate is the weighted average 67.9. So, I mean, this is a typical Cabell County watershed. Curve numbers are usually in the neighborhood of 68, unless there's just, there are a few really strange locations that have an inordinate amount of sand, or there are a couple of places with quite a lot of clay, plastic soil that are group D. But so now 67.9, it is overwritten. Like before, where I typed in 68 for the curve number, you can see now it says 67.9. So anytime you have it run a calculator to define a variable, whether it's the watershed area or curve number, it's going to, any place curve number is calculated and read from, it's going to reassign it that value of 67.9 instead of 68. So we could go over to, for example, the hydrologic modeling module. And we previously were just doing the NSS model. So now let's do TR-55. And select basin in order to open up the model. And so now here is a different view of another way to calculate the peak flow rate. So, you know, a few minutes ago we ran through rational and NSS again. Let's find out what does TR-55 predict would be the peak flow for this watershed. Okay, so let's recalculate the time of concentration. What it knows now was based on that previous assumption of 68. It's going to be pretty close, but let's recalculate based on the basin data. We'll still use the SCS method, but now the curve number is 67.928 instead of 68. So click OK. So it slightly modified the time of concentration. The drainage area is known in miles. Okay, rainfall depth. Well, we want to know the 10-year runoff, and we're going to do a 10-year 24-hour storm. So I don't know if there's a built-in calculator for getting the precipitation data, but let's go to precipitation data frequency server. I guess this is one place that WMS could improve in terms of going to get the data for us, because we shouldn't have to go through this process of manually indicating the location, but it won't take too long. I just move the cursor over to Huntington and make sure that I'm zoomed in on the right spot. And then what I want to get is the 24-hour depth 24-hour depth, because we're going to use a type 2 24-hour distribution. Okay, so yeah, it was like right by the mall area. Okay, so it's set to depth, 10-year. So here's the 10-year column down to 24-hour duration, 3.62. So P equals 3.62 inches. Okay, now back to TR-55. Double click on this to bring it up. All right, so rainfall. It assumes 1 inch. No, we want to know what is going to be the response to 3.62 inches of runoff. Okay, so it's got the curve number already calculated. The area, the percent of the watershed that's pond and swamps is 0. Rainfall distribution. Do you remember that West Virginia is in zone 2 for temporal distribution type? Let's see if we can remind ourselves where we saw that map of precipitation. We're in evaporation, getting closer. Boy, it was a long time ago we talked about precipitation. Here it is. This is the map that says which zone you're in. So we're type 2. The whole state is in type 2. If we were doing a watershed in the Gulf Coast, then you'd need to switch it to type 3. If you're doing it in the Pacific Northwest, you'd change it to type 1A. But it's taking that 3.62 inches of depth, and it's saying over what time period should it be distributed. So it's going to do a type 2 distribution for this depth. Okay, so back to WMS, type 2 distribution, and then at the bottom it's calculated the peak discharge. So 301 CFS. 301 CFS is what TR-55 is predicting. So this is like a Goldilocks thing, right? Too high, too low, just right. TR-55 is likely to be more accurate than national streamflow statistics, because what does this TR-55 method know that NSS didn't? NSS only took the area into account. So it says, well, we're just going to predict what the runoff would be based on the fact that most watersheds in the Western Plateau are similar, but they vary in size, and so the peak flow rate is just a function of its size. So, I mean, it's something, but it's not as good as TR-55, because TR-55 takes into account the specific curve number for our watershed. It takes into account the actual rainfall at a given location, and rainfall isn't the same everywhere in the Western Plateau. You know, so we've got a better estimate of rainfall, a better estimate of curve number, and so we can have more faith in this peak discharge of 301 CFS than we could of NSS or rational method. The big weakness of rational method is, you know, how do you calculate the C value? Like, do you remember what we did to calculate or to determine the C value? It wasn't real scientific. It wasn't based on locally applicable GIS data. The way that we picked the C value to use was we just said, it's steep and it's wooded. I mean, these are pretty big increments to go from moderate slope at 0.25 to steep slope at 0.35. I mean, it's not completely worthless. It's not meaningless. I mean, there is some value in this rational method, but it's calculating the C value of the watershed is a lot less precise than curve numbers. Like what we just did with curve numbers, there are literally hundreds of polygons in our watershed covering about a dozen different combinations of land use and soil types. And so we can, and it's reproducible. It's, you know, justifiable. You know, you can make an argument that this is like a meaningful soil survey and meaningful land use characterizations. And so this curve number calculation has a quantitative basis rather than just engineering judgment coupled with a regulatory table. All right. So that's all I wanted to share with you today, is just refreshing your memory of the workflow, how to do TR-55. And so your homework assignment, if we just take another look at that, for Monday, you need to make yourself a tutorial. So you're writing to your future self and also to me, obviously. What is the process that you go through in order to delineate a watershed and then apply the rational method, apply national stream flow statistics, and to apply TR-55? We've done all three today, so I think you can generate this tutorial pretty quickly. Was there a question in the back?
Yeah, the NOAA Atlas.
Yeah.
There's actually a button on there that will get it for you.
For TR-55?
Yeah, right there. Should be right above type 2. Think compute or
Oh, it's
data.
not on yours.
You guys have it, but I don't?
Yeah, it's right below.
Yeah.
Right
Okay.
below the rainfall, it says run.
So I guess that's maybe what they did in version 11.2, right? Because I'm running 11.1. I guess that's a good reason for me to update.
That's it. Click on it and then pick your storm type, and it already has your.
It's got the location.
And it loads it in.
See, here I was telling that they needed to improve something, and they went and did it. They read my mind. So thank you for letting me know. All right, so we'll have an exam on Monday. I'll see you then.